Okay, for what we have in section 1.7, okay, we have starting off a piecewise defined function appears before us. Now we have a function h that is defined in piecewise terms. And so we have, just looking at the breakdown, okay, you have h of x equals 1/2 of x minus 1 if x is less than or equal to negative 2. And we have h of x is equal to the negative of the square of x plus 1, followed by the additional 1 if negative 2 is less than x is less than or equal to 2. And we have the h of x is equal to 4 for those values of x greater than 2. All right. And looking for h of negative 3. Okay, now we have for h of negative 3. Okay, if you notice negative 3, that's going to be our x value. Now, negative 3 is less than negative 2, so negative 3 does belong to this first inequality statement. And in terms of what to do with negative 3, I'm going to take 1/2 of that. So you have 1/2 of negative 3 minus 1. Half of negative 3 is negative 3/2. Take away 1, and we have negative 3/2 minus 2/2. So we have for h of negative 3, this is going to end up at minus 5/2. Now for h of negative 1 is going to be between negative 2 and positive 2. So negative 2 is less than 1 is less than or equal to 2. Okay, we're going to apply, in this case, this particular part of the function. So we have the negative of negative 1 plus 1 quantity squared, followed by the addition of 1. Negative 1 plus 1 is 0, and we have 0 plus 1 is equal to 1. So we have for h of negative 1, this comes out to positive 1. Now for h of 2, guess what? For 2 cannot be greater than itself, and it cannot be less than itself, but it is equal, and the equal sign belongs in the second inequality statement. So I'm going to apply the middle function. So you're going to have the negative of 2 plus 1 to the second. We have adding to 1. So we have 2 plus 1 is 3. So we have the negative of the square of 3, followed by the addition of 1. So we're going to have 3 squared is 9. But now the opposite side, we have negative 9 plus 1. And so we have for this output, we end up at minus 8. All right, so h of 2 is equal to negative 8. All right, now for what we have in the second question, it says to determine the intervals on which the function is strictly increasing. And we're looking at this in terms of reading the graph in order from left to right. So we have, so I'm just going to kind of do a little bit of coding here. So you have D is for decrease, C is for where the graph is constant, and I would say we have for the increase. Okay, so we had just for the trend reading from left to right. So we have first part, looks like we have the graph is falling. So we have a decrease. Next we have a constant. Then where we have a line segment to be increasing. Okay, we have in this particular section, then we have followed by a constant, and then we have another increase. So we have in terms of where the function is strictly increasing. So we have in this particular case, right? So we have so you have between x at 0 and x at 1. Now, so you have for your second and last increase, you have between x at 5 and x at 7. Okay, and in terms of what we have for the results here, it says to determine the intervals. And the intervals will be in reference to what we have in x. So we have for the answer itself. Okay, putting in interval terms. Now I'm not going to include the endpoints. So you have between 0 and 1. And the intervals will be separated with commas Okay, so you have between 0 and 1, and then we have also between 5 and 7. Okay, and so what I have here, okay, again, so we're looking at strict increase for these two sections, and we have symbolized in terms of the activity of increase, so I have between 0 and 1 for x, and also between 5 and 7. All right, now for what we have in the case question number 3, okay, so we're looking at, for this particular graph, okay, we're looking at, it says use the graph to find the following. It says if there is more than one answer, separate them with commas. So we're looking at all local minimum values of g. Okay, now for minimum values, okay, we have for minimum values, okay, we have where the graph dips, okay, so over here and also over here. So in the case of all local minimum values of g, okay, we have for the first part, okay, we have so you got y is equal to -3, and also we have y is equal to 0. So the local minimum values, okay, we have at -3 and 0. And for all values of which g has the local minimum, okay, that's going to be in reference to the x values that correspond. So you have whenever y is at -3, the x value is at -2. And when y is equal to 0, okay, where we have this particular dip, okay, we have the x is equal to 3. Okay, so you have all values which g has a local minimum. So you have x equal to -2 as well as 0. Okay. Now, in the case of what we have with question number 4, it says to suppose that the function f is defined for all real numbers as follows. Okay, so we have f of x is equal to 1 if x is less than or equal to -2. All right, so f of x, this is just a functional notation for what we otherwise say is going to be y. So you have y is equal to 1 if x is less than or equal to -2. So we're going to have a solid point here thanks to the inequality being inclusive of the equal sign. Okay, and so we have for this particular function, okay, so for the values of x less than or equal to 2, so we're going to have for the y value, okay, that is going to remain fixed at 1. Okay, and then we have f of x is equal to x if -2 is less than x is less than 2. Okay, so for what I'm going to have for the correspondence here, so f of x, so -2 is less than x is less than 2. Okay, now if you notice you have -2 is less than x, and if I have that y is equal to -2 when x is -2, now I'm not going to have a solid point, instead I'm going to have an open circle. Likewise, where y is equal to 2, okay, whenever x is 2, I'm going to have another open circle, and we have just everything else in between. You have like 0, 0, 1, 1, -1, -1. So the second portion that we have here, okay, so we have a line segment between the open circles. Okay, so you have this resulting graph, and then we have in the follow through. Okay, so we have for y is equal to 1 when x is greater than or equal to 2. So we're going to have, in this particular case, so you have y is equal to 1 starting at x is equal to 2. So we have, thanks to the inequality, we have a solid point here. And we have, for the rest of the graph, can we just have a ray that is going to go out to the right. So that will complete the graph of what we have for this piecewise defined function in problem number 4. And now, and say that we have for question number 5, it says, suppose that the function f is defined for all real numbers as follows. So we have in the first case, all right, so we have f of x is equal to x squared plus 1 if x is less than 1. Okay, so we have, so for x is less than 1, you have like 1 squared plus 1 is going to be 2. Okay, and now we're going to have an open circle here. And then for x squared plus 1, say if I have 0 squared is 0 plus 1. And I have -1 squared is going to be positive 1 plus 1 is 2. So you have like 1, 2. Negative 2 squared is 4 plus 1 is 5. So you have like negative 2, 5. Negative 3 squared is 9 plus 1 is 10. And we have like negative 4 squared is going to be 16 plus 1. So I'm kind of out of the zone here. Okay, so we have just for the setup that we have for the first portion of the piecewise defined function. Okay, so you have this particular set of points. Now, we have that f of x is equal to 2 if x is equal to 1. Okay, so if x is equal to 1, and we have that f of x is equal to 2. Okay, so that hole is going to be filled. And then for 8 minus 3x, if x is greater than 1. Okay, so for x is greater than 1. Okay, so we have, so we're going to have, for 8 minus 3 times 1, you're going to have 5. Since x is greater than 1, we're going to start out with an open circle. Then it's have 8 minus 3 times 2. 3 times 2 is 6. 8 minus 6 is 2. So we're going to have at 2, 2. And you're going to have a pattern. Okay, we're going to have a slope of negative 3. Okay, and so for the rest of the graph that we have here, number 6, okay, it says to decide whether we have an even function, odd function, or neither. Okay, now we have in this particular layout, okay, so we have for odd functions, okay, so you have for f of x equals 1 over 6x cubed, and I take the opposite sign input. Okay, and what's going to arise in this one? Okay, so you have opposite sign input. And then we have a positive and a negative 1 over 6x cubed. So you have an opposite sign output. And if you have an opposite sign input leading to an opposite sign output, that's going to define what we have in the case of an odd function. Okay. Now, in the case of g of x, okay, so we're going to start out with opposite sign input. And to see how the outputs are going to end up. Okay, so we have in this particular regard. Okay, so you have g of x. So we have the cubic root of 7x squared. For g of negative x, I have the cubic root of 7 times the square of negative x. And guess what? Square of a negative is going to be a positive. So I have the cubic root of 7x squared. So these are going to end up as the same. Okay, so if we have opposite sign inputs to lead to the same output, this is going to define what we have in the case of an even function. Okay, so the next one is going to be even. And we have, in the case of h of x, you have, for this one, you have x times the absolute value of x plus 4. And if I take what I have for h of negative x, I'm going to have negative x times negative x plus 4, or negative x times 4 minus x. And these are not even the same. They're not even additive inverses of each other. And so for what we're going to have in this case is neither.